All right, welcome everyone to the AQT Colloquium series. Today, it's our pleasure to host Dr. Gregory Quiros. Greg Quiros is a senior scientist at the Johns Hopkins University Applied Physics Laboratory. In addition, he holds an adjunct professor position in the Physics and Astronomy Department at Johns Hopkins University. Dr. Quiros received his PhD from the University of Southern California in 2013, where he studied quantum control and adiabatic quantum computation. Thereafter, he transitioned into a role as a staff scientist at the Aerospace Corporation in Los Angeles, California, and his current focus, his research there focused on quantum communication and quantum algorithm development for national security space applications. Since 2016, he has been a senior scientist at the Johns Hopkins University Applied Physics Laboratory, where he now also holds the role of supervisor for the quantum exploitation section within the R&D sector of the lab. His current research interests include quantum characterization and control, applications of quantum control to quantum algorithm design, and quantum sensing. Greg, please take it away. And for the audience, Greg has expressed interest to withhold questions until the end. And once he's done with the talk, we'll take questions. Please.
Thank you, Kasper, for the nice introduction. And thank you for inviting me to give a talk here today. So today I will be talking about some of our work that was published at the end of last year that focused on quantum crosstalk robust quantum control. I will discuss mostly that work, and then at the end, I will talk about some of our recent results, which are extensions of this particular work. So I will get going here now. Let me see. Okay, there you go. So what we were essentially trying to do is we wanted to develop some general conditions for quantum crosstalk suppression. And we wanted to do it from, from this control perspective. One, as Kasper mentioned, my general area of expertise is in quantum control. So for me, it was sort of natural to kind of start from this perspective. But also, it is something that if we can derive these types of conditions, then we can actually extend it into many different directions, and I'll show you a couple of those directions here today. Now, while the goal is to derive more general conditions for quantum crosstalk suppression, today I will talk about just the derivation of conditions for first-order suppression, first-order in time-dependent perturbation theory, and we'll focus specifically on single qubit operations that are applied simultaneously. Okay. So the motivation for this work was that there are many different types of strategies that currently exist for dealing with quantum crosstalk. From a hardware perspective, this can be done by introducing tunable couplers, introducing tunable, flex tunable qubits, and so you have systems right now, for example, like IBM's IBM Quantum Experience, where these systems are typically fixed frequency qubits with fixed couplers, and those systems, of course, are very, very much susceptible to crosstalk. And as I mentioned, there are different ways in which one can overcome this in the design of the hardware itself. Now, of course, crosstalk doesn't only happen, at least these types of quantum crosstalk interactions don't only happen in systems like superconducting qubits. They can happen in many different types of systems. For example, trapped ions also exhibit these, as well as neutral atoms and so on. And so, the current approaches that exist when it comes to things like superconducting qubits, are very much platform specific, right? And so for those that are more on the user side of things, if you are given a particular piece of hardware, you can't really, let's say, you can't really use these types of hardware related approaches to mitigate crosstalk, as being someone that has no ability to let's say to augment the architecture that you're given, right? So there are many ways, of course, in which one can deal with crosstalk when it comes to the software side of things. And a lot of these approaches that have been designed thus far have been primarily focused on sort of what can you do with compilation? How do you account for crosstalk and sort of how you transpile your gates, how you compile your gate operations, how you schedule your pulses even. And while there has been, I'd say, while these approaches are very useful, they are very much, let's say, rooted in sort of optimization routines, and don't really provide a lot of insight into how, let's say if you get certain types of crosstalk suppression, how that actually extends, and how you can sort of use that as a way to understand more broadly how to achieve crosstalk suppression. And so our goal here was really to try to gain some more intuition into broader principles of what it means to suppress crosstalk, and how we can extend those broader principles to specific applications. So let me first give you an idea of, I guess, an outline of some of the theoretical aspects first. So the model that we considered is a model where you have basically a Hamiltonian that has two parts to it. One is your control Hamiltonian, and one is a Hamiltonian that is going to be in charge of the noise that you're subject to. Now, we assume in our model that we have amplitude and phase control so that we can move ourselves anywhere on the Bloch sphere. When it comes to the noise, we assume that we have two components of noise. The first one is we assume that we have local noise, which acts on each individual qubit. And this is represented by a mean field approximation to your environmental noise, where we have some statistical fluctuation, some statistically varying field, and we make assumptions of white sense stationary and zero mean. The zero mean part of it is not necessarily required. The white sense stationary part of this just sort of makes the math a little bit more agreeable. This type of noise is assumed to be local on each qubit. And this is something that shows up in a lot of different types of systems. It's not sort of a model that we've just sort of chosen arbitrarily. These types of noise processes that are represent temporally correlated noise are quite common. For example, they can be found in superconducting qubit systems. Quantum dot systems are also ones that exhibit similar types of noise. One thing that those of you that are familiar with superconducting qubits, as of course AQT AQT very much so is, you have these temporally correlated noise processes that are typically 1/f like in nature. And so this constitutes the noise that we consider locally on our system. And then in addition to that, we assume that we have a static crosstalk term. And this is the part that takes into account all of the static quantum crosstalk. In the model that I'm showing here, the noise is assumed to be just ZZ interactions. And this is basically just for sort of ease of representation. In the paper, we show that the conditions that we derive and so on are actually something that extend beyond just ZZ crosstalk. We can actually look at sort of any type of crosstalk model, and still our conditions still can be derived. So using this model, what we do is we want to derive, as I mentioned, conditions on the crosstalk, on crosstalk suppression in particular. So the way that we do this is use sort of a canonical approach, where we assume that our noise is weak relative to the control that we're applying. And so therefore we move into a rotating reference frame with respect to our control. And we analyze the dynamics of this rotated frame noise Hamiltonian say we examine it perturbatively here, and then try to draw conclusions from the perturbation theory on how we need to suppress this noise. So what we do here is, as I said, we move into this rotating frame, and by doing that, what this does is it induces rotations on the individual qubit components. And from that, actually, an important part comes out, which is this R of T function, which is known as commonly as the control matrix, sometimes known as a switching function, and is commonly seen in things like filter function formalisms and so on, if you're familiar with this sort of language and control. Now, with this this rotated frame Hamiltonian, we can start to examine the dynamics of in different ways. So, for example, we can examine the dynamics of, let's say, an observable, and we can look at the noise average dynamics, where the noise averaging here is averaged over these classical degrees of freedom here that can be stochastic fields. Now, if we do this expansion to second order, the noise, we can actually isolate the noise solely into this exponential here. And it is composed, notice, of two terms. One is the first order contribution and the second order contribution. And the first order contribution here corresponds to is proportional to the mean of the noise. And the second order contribution is proportional to the variance. Now, because of the way the model has been developed, it turns out that that the first order contribution is solely has contributions of crosstalk, and that is just plainly just because of the fact that our crosstalk model assumes that our crosstalk is static. Whereas with the zero mean assumption that we've made on our temporally correlated noise, this implies that the second order term, or the second cumulant here, is going to house essentially all of our temporally correlated noise. So in this way, we've it's kind of conveniently partitioned out our contributions of crosstalk and our contributions of the temporally correlated noise. Now, as I mentioned, the first order term, which is of course going to be the dominant term, is going to be proportional to the quantum crosstalk. Now, on the top right, I show an expression there for a general expression for the first order, the first cumulant contribution. And while the specifics of it aren't necessarily important, what I want to point out here is that essentially there is a function that we can define, this chi here, which is going to be dependent on the qubit indices ij and sort of the Pauli operators that couple to it, which are here written in terms of mu and nu. And what this thing is essentially a function that calculates sort of the overlap in time, the overlap in time between the switching functions between two qubits that are next to each other, right? And so, sort of broadly speaking, one can see that in order to obtain first order crosstalk suppression here, that one can simply just one can say here that if chi can be set to 0 for all mu, nu, and I and j, then we have first order crosstalk suppression. And so the idea here, essentially, what I'm going to show you is that that this condition here can actually get us to many different applications where we can actually see pretty significant impact from the cancellation of crosstalk, or cancellation of just this first order term. So the first, so me being someone who works in control, my first thought of where to try this out was in dynamical decoupling, and therefore, preserving quantum memory. And so what we wanted to do was we wanted to examine our ability to suppress crosstalk on a collection of qubits. Actually, I'll say crosstalk in any other sort of noise present. In this case, any noise present that is correlated in time. And we wanted to do this using dynamical decoupling, but we wanted to do this on a collection, as I mentioned, of n qubits simultaneously. Now, in order to obtain crosstalk suppression, first order crosstalk suppression, we can show that if we were to take our dynamical decoupling sequences, and let's say here, for example, I take an XY4 sequence, which is a well-known decoupling sequence, which involves the alternation of X pi pulses and Y pi pulses. If I were to take this sequence and I were to shift the sequence such that no two pulses are overlapping, then it turns out that I can show in the limit of finite width pulses that this will satisfy this crosstalk suppression criteria. And interestingly, some of our more recent work has shown that this sort of staggering behavior is not limited to XY4. And in fact, you can actually do this with essentially any dynamical decoupling sequence that you want. We don't have rigorous proofs of this yet, but at least empirically, this is what we're finding that to be true. Now, if you were to, so the rationale behind this is kind of the following, is that if you allow the pulses to overlap with each other, let's say directly overlap with each other, then what would end up happening is, from a dynamical decoupling perspective, is you wouldn't be able to get this sort of modulation required to average out the noise. So essentially the quantum crosstalk term, which is that sort of that term that links the two qubits together, you would find that essentially every time you applied simultaneous pulses, you would end up basically having sort of a static modulation. So in some sense, it would just be as if the quantum crosstalk is sort of left preserved and everything else is being decoupled. So that's kind of the basic idea of kind of why we stagger. We stagger so that we can effectively average out these interaction terms. Now, up on the right top right corner, I show an example here for 5 qubits where we show how we can stagger these sequences. So what we do is we solve essentially a graph coloring problem where we have 2 colors. And on hardware like IBM's hardware, this is pretty straightforward, right? So we can take like a 5 qubit system here and we can just sort of alternate between these 2 sequences. And if we now say, let me prepare the qubits in some arbitrary state, and let me try to preserve that qubit for some period of time, applying repetitions of these dynamical decoupling sequences, returning the sequences back to the ground state and measuring, how well can I obtain that ground state after some number of repetitions? Here we do a comparison to where we look at the case of free evolution, which is where we have just purely idle evolution. And we compare this to the case of simultaneous XY4 sequences. And then we compare this to the crosstalk or the crosstalk robust or the staggered DD sequences that I show here. And so what you can see here is that from this crosstalk suppression alone, we obtain a pretty substantial improvement in the decay rate of the qubits. So, this was sort of one of these sort of simple experiments that showed us that, well, this sort of first order suppression can be quite significant, at least in these types of IBM systems that are available. Now, of course, we wanted to go beyond 5 qubits, and so we started to look at larger processors. And in the bottom plot, we show here a comparison of the decay rates, which are determined by performing fits to each one of these lines, according to this fitting function here. And here we show with the blue dots here, or the blue symbols here, we show the decay ratio. So the ratios between doing the CR sequences and doing the XY4 sequences. And what you can see here is that as we increase the number of qubits, even just going from 2 to 6 qubits here, we see a pretty substantial increase in our ability to suppress crosstalk. And actually, we see the impact, right? The pretty substantial impact. And in fact, you go from about with 2 qubits about equivalent performance between the 2 sequences up to about 3.5 times better in the decay rate. And while there is some variation in this as we increase the number of qubits, we see that on average we're about a factor of 3 better in our decay rate by doing the crosstalk robust sequences versus doing just the simultaneous sequences. So this is meant to to show you that this crosstalk suppression condition can sort of easily be used in dynamical decoupling to already preserve qubits when you have a set of qubits that are next to each other and you want to preserve the entire collection of qubits all at once. Now we went further than this and started looking at at characterization instead. And so we wanted to look at what's known as noise spectroscopy. And we wanted to see here if we can show that the crosstalk suppression condition also applies for noise spectroscopy. So I'm not going to get into the specifics of noise spectroscopy, but I will give you an idea of what it is. So for those, of course, that are not familiar with it. The idea here is that you use your quantum system, or let's say here your qubit, you use it as a dynamical probe. You apply a series of control pulses to the system, and the idea is that by applying these pulses, you tune the frequency response of the qubit. And in cases where you may have noise that is, let's say, broadband, the idea is that by changing these pulse sequences and by tuning the frequency susceptibility of the qubit, you can sort of scan a wide range of the environmental noise, and you can sort of back out a noise power spectral density for the noise that is plaguing your qubit. And so what we wanted to do here was, again, apply this type of crosstalk suppression criteria. We wanted to apply it to this problem of characterizing the environmental PSD. So of course, we can start by looking at environmental noise, but it's actually better if we can sort of benchmark the protocol on noise that we've injected into the system. So what we do is we use a protocol that we had developed earlier on that allows us to inject dephasing noise. Essentially, the way it works is that after each gate we apply these RZ rotations, which on superconducting qubit systems are just frame changes. And what we do is our injection technique tells us sort of how to choose these angles of rotation such that we can produce the power spectral density that we want. And so what we do here is we say, let us inject noise that is narrow band and has different center frequencies depending upon the qubit that we are injecting it upon. So here's an example for 5 qubits. We would say, 5 different qubits with 5 different frequencies. Now, we use a particular noise spectroscopy protocol, which is known as the fixed total time pulse sequences. The specifications of it don't matter, to get the point across, but I did want to mention it here. When we try to implement this protocol without the crosstalk robustness, and try to perform the reconstructions of these noise power spectral densities, from this noise spectroscopy protocol, we see that on 7 qubits, we get sort of basically the plot that I show here, sort of just essentially nonsense. Now, the noise that we injected onto the system is actually shown by these dotted lines here. And so you can see here that we are, quite far from the injected noise. Excuse me, quite far from the injected noise that we impose upon the system. However, if we now reconfigure these noise spectroscopy sequences such that they satisfy this crosstalk suppression criteria, then we actually see dramatic improvements in performance. So just to kind of give you an idea of how this works, the modulation sequences that we use for the noise spectroscopy protocol are essentially related to the zeros of the cosine function. And so we can use this fact that the sequences themselves are derived from the cosine function to say very trivially that if we were to now build a similar type sequence but derived from the sine sequence, then we can achieve this cancellation of this crosstalk term. If you remember, this chi function, as I mentioned, was essentially an integral in time, with an overlap between the switching functions between 2 neighboring qubits. So if I make one of those a cosine and one of those a sine, I will naturally get cancellation. And so that's essentially the way that we design these sequences. And if we pattern them across a chip, in this case, this is a 7-qubit processor. If we pattern them across the chip, we can actually do simultaneous noise spectroscopy on all 7 qubits here, and you can see the results are dramatically better. So again, the dotted lines here correspond to the noise that we've injected. The solid lines correspond to the mean. We actually performed these experiments over 5 different realizations over 5 different days. And the shaded regions correspond to the 95% confidence intervals in our reconstruction accuracy. So, this is I think was even sort of a more compelling result for the crosstalk suppression in the sense that we essentially could not do simultaneous noise spectroscopy on 7 qubits if it were not for the suppression of this first order term. And we have a explanation for this, and I'm happy to go into that more. But essentially, you can think of it as that what happens is in order for us to actually do the suppression, or sorry, in order for us to actually do the reconstructions, we run these probe sequences on run these probe sequences on the qubit. We extract survival probabilities for the qubit, and then we use those survival probabilities to do the reconstructions. Essentially, what happens is when you have crosstalk present, it sort of shifts. It creates vertical shifts in the survival probabilities that can actually wash out a lot of the really interesting spectral features, especially those that we've injected in this case. And so it sort of makes it such that it's impossible to see the interesting features of the noise that either we're injecting or that is present natively. And so when we perform reconstructions, we essentially see flat lines. We see sort of survival probabilities that look like we're measuring one sort of, instead of, if we think we're measuring, if we wanted to measure the 0 state, it looks like we measured the 1 state. So sort of these very interesting sort of alterations to the survival probabilities that really mess with our ability to do the reconstructions accurately. So the next thing that we've been doing, I'll say right here that this is sort of, this sort of concludes the stuff that we've included in this paper that I had mentioned. In more recent months, we've been going beyond this and thinking about how we can now use this crosstalk suppression criteria in the design of our gates. So we have this method that we created a while back, known as filter graphs or filter gradient ascent and function space. And the idea is that you want to build optimized control waveforms that provide robustness to temporally correlated noise. Okay. And so the way that we do this is we assume that one is given some information about the power spectral density, at least enough knowledge to say that we know where the noise is predominantly focused. And so, we can identify sort of regimes where the noise is weak enough that, we can, let's say that we want our controls to live, that we're okay with them living there. And so once we can identify these sort of regimes, then we can start to ask questions about how do we build controls that put us into regimes where the noise is weak. We find in this work that the bandwidth of the controls that we have to use is very much related to sort of where this cutoff frequency is that we set. In fact, it is very Nyquist-like, in that typically it needs to be about twice as large. And I refer you to this paper if you want to see more information about this. The type of sequences that we use in order to construct our pulses, we use a functional basis, and we use the Slepian, what known as Slepian sequences. And these are band-limited functions that are optimally concentrated in frequency space. And so the nice thing about them is that they inherently give us a way of controlling the bandwidth of the basis functions that we use to derive our control. So that is to say, that if we know that our control hardware has certain limitations in bandwidth, we can impose that directly and intrinsically onto the basis that we use to define our control, and therefore when we do the optimization, it is intrinsically satisfied. So these are kind of a nice basis for this reason. What we do is once we define our pulses in this way, we can define certain types of initial conditions in our controls that give us sort of initially good guesses about where we need to put our controls, at least spectrally speaking. And then from that, then we can use this gradient-based optimization technique to derive controls, which sort of give us qubit responses. These are filter functions, but essentially, these are just the frequency response of the qubit to a particular control. We can tailor the response so that it's outside of this band that we are trying to suppress the control within. Essentially, we can create controls with high pass features, with band pass features, and so on. So we took this work and we wanted to extend it beyond just temporally correlated noise and start to ask questions about dealing with simultaneous operations where we have, simultaneous gates on 2 qubits. And so therefore we wanted to start addressing problems of crosstalk. So we start to look at this problem again from a very similar Hamiltonian that I showed you before, where we assume in this case that we have amplitude control, and again we have our temporally correlated noise, which fits again within the filter graphs construction, and we add an additional term here, which is our ZZ crosstalk. And now what we do is we look to build controls which solve an optimization problem where they produce a particular target gate that we want to produce. And at the same time, they minimize the spectral overlap here. So this accounts for the temporally correlated noise. So minimize the spectral overlap that we have in particular in this band where the noise is most prominent. And then at the same time, we also want to minimize the noise due to the crosstalk. And this is this chi function that I had shown you earlier, defining the crosstalk suppression condition. So we can show that this, we can do this on 2 qubits. We can come up with controls which give us high pass features here. You can see this is for 2 qubits. The shaded regions here correspond to the regimes where the noise is dominant and we want to cancel. And so we can create, simultaneous high pass filters on 2 qubits while canceling crosstalk. We can also do band pass, where in this case, for example, the one on the bottom shows that the red qubit 1 here shown in red is canceling it's a high pass filter. It's canceling everything at low frequency, and qubit 2 here shown in blue has some sort of high, let's say, spectral features at higher frequencies, and so we need to cancel noise within that regime as well. So more band pass like. So we can kind of play this game, and we can show that that we can provide both spectral suppression of the noise as well as crosstalk. So we wanted to show that this was the case, and that that this was the case beyond just numerics, of course, in experiment, right? And so what we did was we built a gate set that satisfies these conditions, these crosstalk suppression conditions, and the gate set was specific to the superconducting qubit platform that we have at the Applied Physics Lab. So we have fixed frequency and fixed coupler qubits. And so, in our case, we use identity gates as well as square root of x gates, and of course also pi gates as well, x pi gates as well. So, when you think about sort of building this gate set, before I even get to sort of the experimental results, when you think about building this gate set, one may think, okay, well, if I have to worry about crosstalk suppression, it seems that I have to consider all possible combinations of these gates. And if I have, if I start increasing in the number of qubits, then those combinations increases as well, seemingly exponentially. And so, you may ask questions about whether or not, building these gate sets which have crosstalk suppression built in them are actually feasible as you increase the number of qubits. And so it turns out that by making a fairly straightforward, well, I'll say it's a straightforward argument, but in a fairly straightforward way, we can show that by using simple ideas in graph theory, that we can build a gate set that scales independently of the number of qubits, but is dependent upon the topology or the specifications of the topology of the hardware. And so in this way, we can actually build scalable gate sets that provide crosstalk suppression as well as temporally correlated noise suppression. Now, here I show you an example of an implementation of this gate set on our superconducting qubit system. So shown on the left are our gates here. These gates actually this is actually some of our earlier attempts at this. where these gates are about 120 nanoseconds. Now we actually have this down to about I believe 50 nanoseconds, if not shorter. But here's an example of the type of pulse waveforms that we get from our filter graphs optimization with crosstalk suppression, and an experiment here that shows these pulses in action. So what we do is we again go back to our dynamical decoupling sequence, and we say, previously, if I know that if I were to apply these XY4 sequences simultaneously, that I would preserve crosstalk. So if I do this using sort of a standard Gaussian pulse, I get no crosstalk suppression, and you see what you expect: oscillations in the survival probabilities of the qubits corresponding to the presence of crosstalk. However, if you change those optimized pulses, or change those pulses for the optimized pulses, then what you see is now we have crosstalk suppression, and so now you can see that the survival probability sort of rides along the top of this curve, which is essentially an artifact of the fact that we are now canceling our crosstalk. Right now, we are going beyond this, going to more qubits, looking at simultaneous characterization experiments, sort of broadening the scope of what we can do, because now this sort of first experiment was a great way to show that essentially that we can do simultaneous operations with crosstalk suppression, and this sort of opens up a fairly wide range of the things that we can do simultaneously on our qubits.
Can I ask a question?
Yes, go ahead.
I noticed your gates have very sharp features in them. Don't you worry that something like this would introduce a lot of harmonic tones that could lead to crosstalk to other qubits if you have many in a register? I mean, I personally would never even put like a square pulse into our system, and this has like many square pulses. So have you guys looked at like, what's the kind of the frequency spectrum that you're putting in?
Right. So we have, and actually I'll say here to maybe somewhat put your mind at ease, that our pulses now, so this was an earlier attempt. So I'm showing you results here that maybe you'll appreciate have been approved for release. We have much more recent results where we have the pulses are much smoother. And as I mentioned, they are down to maybe about half, if not even shorter than the current pulses I'm showing here. And they don't have these sharp features that you mentioned here. In our experiments, here we're doing, we have just the 2-qubit case. We've extended beyond that to multi-qubit, and we don't see any current issues, at least as we scale up. But we're not, we're doing this on up to 4 to 5 qubits. So we're not, it's not a significantly large number of qubits.
Great, thanks for that. And just briefly, do you have the ability to monitor leakage? Like, do you know if some of these waveforms you put out could actually be potentially driving leakage on other qubits, like coherent leakage?
Yeah, that's a great question. We've in our recent experiments, we have also looked at leakage too, to see, and we do not see a substantial amount of leakage. We're not optimizing for leakage, but we do not see a substantial amount. I think at 50 nanoseconds, I don't suspect that we would see as much. If we started pushing this down to past beyond 35 nanoseconds, I would expect to start seeing more. I think our pulses are so long right now that I think that we just don't see much, of a contribution to leakage or from leakage.
Okay, thank you.
Okay. So actually, I'm about to end here, so I will be happy to take more questions here in a second. So what I've tried to show here today is that we can that we've derived a suppression condition for first order crosstalk suppression, and it's something that we can actually use in a variety of different applications. So we've shown it for doing simultaneous control on multiple qubits, for doing noise characterization on multiple qubits. And now we've gone beyond sort of the initial dynamical decoupling experiments and gone more towards actually the design of our gates. And so now, as I mentioned, we are currently looking more into this to see sort of what's the impact that we can have on quantum algorithms. and also various types of scenarios with multi-qubit simultaneous characterization experiments. From a theoretical end, we're pushing more into how do we use this crosstalk suppression condition to inform algorithm design, and how can we come up with sets of rules or guidelines that one would want to follow when designing quantum algorithms. So with that, I just want to acknowledge the students and our collaborators whom without them, our work wouldn't be possible. So thank you, and I'm happy to take questions.
All right, let's thank Greg for a nice talk. And yes, the floor is open. I see Jan is already very curious. I knew you would. I knew you would jump in, Jan. Please go ahead.
Hello. It was very interesting talk. Can you tell me how many parameters, when you characterize the crosstalk, how many parameters do you reserve for qubit to do the characterization? Let's say for your 4-qubit chip, how many numbers it is?
So when you say crosstalk characterization, so we are not characterizing the crosstalk in any of our experiments. So the condition is satisfied under the assumption that the crosstalk is present, but we do not characterize the strength of the crosstalk in order to achieve the condition.
Well, so does it mean that if you, for every circuit you run, you would have a different optimization procedure? So for any combination of gates, you will have a different corrections, which are not computed without doing the measurement itself?
Okay, so you're talking about the optimized gates?
Yes.
Okay. So let me. So yeah. So the filter graphs. So when we solve this problem using filter graphs, right? This crosstalk suppression condition that we impose here in the optimization, these JIJs that we have inside this chi-ij, right? All of this stuff is done in an open loop fashion, right? So we solve the optimization problem offline. And then once we obtain these pulses, the pulse, the waveforms themselves, then we go and we have to calibrate these pulses on hardware, right? So, but as long as we can keep the relative shape of the pulses the same, and rather we're just sort of amplifying the amplitude of the pulses, then our crosstalk suppression criteria should be still satisfied. So it doesn't require us to actually characterize the crosstalk coupling in order for us to get the suppression, because as long as the pulses remain in line, which of course is not always easy and it's not always guaranteed, as long as they remain in line with the assumptions we made in the optimization, the offline optimization, then we will still see the suppression. And that is exactly what has happened here. When we do the optimization does not take into account these JIJs in any form. It's done offline, assuming that we are just trying to satisfy the minimization of this overlap in these switching functions. If we have that sort of condition satisfied, then when we tune the pulses up, as long as we don't lose the shape, then we will get the suppression that we expect, and that is what this plot shows here. So,
thank you.
You're welcome. Yeah, I will say that of course, calibrations fall out of tune and so on, and if our calibration drifts too far, then we will start to see more crosstalk again. But the actual optimization is not dependent upon that. Dependent upon knowing specifications of the crosstalk.
I have another question. So one of the reasons crosstalk is hard is because of the presence of context-dependent errors. So let's say you calibrate two square root of x gates such that they are crosstalk robust, but now you place them in an algorithm where you decompose them into ZXZXZ or however you want to do this, and the nature of the crosstalk between these two gates is different because of the phases in front of them. Do you have ways of dealing with this, or do you just hope that on average it is better?
So Our design relies on, for example, here, let's say that these, actually we show here, let's say that these X gates correspond to your square root of X gates that you're applying, and maybe these Y gates here, let's say these Y gates are these phase gates that you're talking about, right? The only thing that we can guarantee is that we are getting suppression while these gates are being implemented. That is the only suppression that we can guarantee in this implementation. So we will get local suppression of crosstalk on each one of these X gates. Anything that is due to crosstalk that occurs over longer ranges is not dealt with.
I guess what I mean, not necessarily over longer ranges, but the moment your input state to these, like prior to these gates, is now different, then the nature of crosstalk between the gates will also be different. Best thing I can say is like a nature of crosstalk between X and Y is going to be different. But now this becomes more complicated as you have like potentially random gates, which you decompose to local operations. That's what's the term, like context dependent. Like the nature of the errors are dependent on the context of the gates. So I'm just like, just curious if you guys have explored this at all, and how robust your method is to different errors in different contexts.
Right. So we construct the optimized gates from whatever gate set is given. So if you know you're transpiling down to identity square root of X, let's say square root of X is the only gate that you care about, or square root of X in an X gate. Then we would optimize with respect to those particular gates. So when you transpile any general unitary down into your square root of X gates, then because the optimization is done on the unitary, not on a particular state dependent metric, any state that is passed through should in principle be should be okay, essentially. So the gate set itself is what is optimized. So I don't think that we will have, I think the only context dependence that we're worried about is what gates we're applying simultaneously. And that is the only thing that should affect the efficacy of these gates.
Thank you.
And I'm happy to talk more at some other point. If I didn't answer your question, I'm happy to to go into more detail.
Any other questions? All right, Greg. You mentioned that these are the bits of your work that have been approved for public release. Where else are you taking this?
Right. Yeah. So right now we're looking at doing we're looking at implementing this in algorithms on hardware, our own hardware. We're looking at doing at least from the hardware side of things, we're looking at implementing these types of things in doing simultaneous characterization experiments, but more diverse characterization experiments. So not limiting right now, the one I showed you was a noise spectroscopy experiment, but there's obviously a much broader range of characterization protocols that exist. And so, we want to know if we were to use these types of gates and start to look at things like RB or GST, and we want to do this, maybe we want to run RB on one qubit and GST on the other, simultaneously, right, across some chip. We want to know how well we can do that, and how well these gates can suppress the crosstalk and allow us to get the information about the individual qubits. So we're moving in that direction, but we haven't gotten there yet. But that is where we're going.
Okay, thank you. If there are no more questions, let's thank Greg one more time. And